Hi, good morning, everyone. Thank you all for joining the seminar today. Today I have the pleasure of introducing Professor Sandra Korte-Kerzel. She did her studies in Aachen, in Christchurch, New Zealand, and in Cambridge. And she's now the chair of materials physics at Aachen, as well as the head of Institute of Physical Metallurgy and Materials Physics. Today we'll be listening to a seminar on new methods and opportunities across the scales, complex crystals, defects, and damage in alloys. So without further ado, I'll now hand over to Sandra.
Yeah, thank you very much. Thanks for the introduction and inviting me. I think we don't normally kind of know each other. I know a few people from your group, but I think it's really nice to have these kind of seminars during the Corona period where you can just go over without traveling. Okay, so first of all, we just heard the title. It was too long, kind of. So I just summarized it. There are three things I want to talk about, and I have an overview slide in a minute. I'll be talking about complex crystals, defects in crystals, and also how we might assess damage in alloys. And there are, of course, a lot of people who contributed to this. These are the people who contributed most, I think. Setare did a lot of the machine learning I'll be telling you about. Carl did a lot of the damage experiments, same as Muhammad. Julien did atomistic simulations. Oli Kerzel, my husband, helped with the machine learning, and Stephanie Zandlöbeshout helped with a lot of the defect kind of strategies and concepts. Okay, so just to start us off, I think we all kind of do the same thing normally when we think about materials. We always have some property that we want to think about, and that can be at the macroscopic scale. And then as materials physicists, scientists, we normally go and say, well, that actually originates from the microstructure. And we can interrogate individual phases, how they deform, and which crystal defects actually give rise to their properties, how they're affected by alloying, and we can do that all the way to the atomic scale these days. We can do that in the experiment, but importantly, I think now we can also go back in scale and use the same scales to not just look at something that's maybe most of the time stationary in the microscope, but to actually look at dynamics using, for example, atomistic simulations. So what we do then a lot of the time in our research is kind of we combine the scales, we try and design materials from the nanoscale, but also from the microstructural scale. And they are kind of all of these length scales I want to just dip into briefly and give you an overview of what we do there. We'll actually have at the macroscopic scale or at the microstructural scale, there's a problem we wanted to address in that most of the time you have very heterogeneous alloys. High performance alloys are intrinsically heterogeneous, and what we always get is that we get to high resolution, but then we're missing the statistics, and that's something we've tried to address using convolutional neural networks. I'd also want to go down a little bit in scale and tell you briefly how we try starting to think about thermodynamics of lattice defects. So not just their structure, but also their thermodynamics. And I'd like to start actually on the smallest scale, thinking about crystal building blocks, which new materials we might actually find if we think about more complex crystals as well. So we start from the bottom here, from the smallest scale, and then work ourselves up. This is actually funded by the European Research Council as part of the starting grant fund blocks. So the first thing to think about from my case, and it depends, I don't know what everyone's background is, so I thought I'd start out kind of with this. What's the role of the crystal itself in deformation? And I think it's actually the most essential role. The crystal structure determines deformation. It actually determines how, in general, a material deforms, whether it's intrinsically hard and brittle or whether it's ductile. And just to show you briefly that it is actually the crystal structure and not so much the elastic modulus or the bonding itself. If you compare two materials with a very similar shear modulus, like silicon and copper, then their intrinsic strength, so not after alloying and all of these things, their intrinsic strength differs by about 4 orders of magnitude. And the reason for that is that if a dislocation wants to move through the lattice, it has to overcome the resistance of the lattice. And that depends actually exponentially on the distance between the slip planes over the Burgers vector, so the jump distance of a dislocation. The bonding, the shear modulus, goes in as well, of course, but it goes in linearly. So it's not as strong an effect on the absolute stress that we are measuring in a material. So what does that mean? Once I know this, that I have the slip plane spacing and the Burgers vector, you might think actually it's easy, right? I want to select my material based on maybe wanting to have something that's fairly strong so I can operate it at high temperature and still have a remaining strength. I just go into a database and look at this, and then I find something where I can maybe increase toughness by lowering the strength a bit. You're looking for something that's appreciable tough, but still strong to look at. And a lot of the materials, actually most materials, are not an aluminium alloy or a titanium alloy or something of the sort, a pure metal that's been alloyed. Most materials in a database will actually be binary, ternary, and so on crystals. And all of these tend to form much more complex crystal structures than just an FCC or a BCC lattice, or they have larger motifs that go on these lattices. So what we want to do is we want to be able to go and look at these structures and predict what their deformation characteristic might be. And for that, we need to understand the mechanism so that we can then predict stresses based on the crystal structure. And there are difficulties, and the main one is that actually you have to know the slip system to do the analysis I just showed you. If you want to measure the distance between two slip planes, you have to know which plane that is, and you have to know which Burgers vector a dislocation might have. And that's something that for most intermetallics, for example, we simply don't know. So what we are doing is we are looking at binary systems and one ternary system as well, where we have very closely related crystal structures with the same elements in them, so that at the end of the day, we can simplify what we are looking at and not just look at a large unit cell, but actually look at common building blocks that we have. These building blocks, for example, are some of the most common ones in intermetallics. So when you see these complex crystal structures like this one here, or these over here, they're actually made of building blocks which are combined. And the dislocation doesn't care about the symmetry of the unit cell as much as the geometry of the slip plane. So we think it's a good approach to think about building blocks and unraveling their mechanisms rather than trying to understand hundreds of thousands of materials which might be different in terms of their unit cell. So this is where we're at the moment, simplifying and understanding mechanisms. And I just want to show you a little bit of where we actually are with this. So in undergraduate teaching, we draw edge dislocations, right? We draw them into a primitive cubic lattice most of the time. We also think about FCC and BCC crystals. But if we look, for example, in Laves phases, that's the crystal that's shown here in one projection, they're the most common intermetallic packing as common phase, but we don't even know how to draw a dislocation in there. It's very difficult to even think about how to draw an extra half plane into this. So that's where we started out at it. There's one example, for example, hexagonal Laves phase, MG2CA. And if you look into the basal plane of this, and you can do some atomistic simulations, because for this we actually have potentials, then we can, of course, look along the plane, and we can look from the top, and we then try to shear the crystal lattice. It actually looks all right, right? You think, yeah, you shear like this, and then you get a stacking fault, and that's probably a good candidate for deformation. However, if you look from the side, then you can see that that's probably not going to happen, because essentially the slip plane has to take off and be moved upwards by a long distance. And so when we actually relaxed these simulations further and looked for the minimum energy path, then what you get is this. And you saw there was some jumping about, so I'm just going to tell you this in a bit more detail. What actually happens here is that you get shift in one direction, and then, as you saw before, atoms collide, right? There are atoms here in this triple layer who are nearly at the same height. And so what happens is that you then have a sideways movement of one plane in this lattice, and then the whole shear movement continues to arrive at a stacking fault. And so this whole process is called synchroshear, and that's what's happening in this simulation. And there are a few difficulties with this. And this all of a sudden, slip is no longer happening in one single plane. It's two adjacent planes, and the atoms also move in two different directions. So also the normal kind of modeling strategies that we use, like a gamma surface, they kind of go out the window in terms of understanding these. I think we have a problem here that's a little bit to comparing soccer to Quidditch. All of a sudden, you're not thinking about one ball and a 2D problem. You have a 3D problem. You have collisions, all sorts of atoms that are actually in the game. So that process, we didn't come up with this process. That process had been known or had been suggested actually quite a while ago. It's called synchro shear, and it was first suggested for sapphire. And then in the 90s, it was suggested that this actually might happen in these Laves phases on the basal plane as well. The problem was that until, well, now maybe not that recently, 16 years ago, nobody had actually seen it. And in 2005, there was a science paper that essentially just looked at a dislocation and showed the stacking fault that's consistent with this mechanism. But of course, that's a stationary defect. It wasn't even necessarily put in by deformation. What's changed over the last few years, and while I think we can now finally go out and maybe try and understand crystal plasticity in these phases, is that we now have experiments that can actually look at this and look at this in a quantitative manner. So we can suppress cracking in small volumes using micropillar compression, and by that we can actually then get deformation, and importantly we can also pull out samples that we can meaningfully put into the TM and analyze all the way to, again, high resolution imaging, where we can find out which dislocations were actually active in our material. So we can measure critical stresses and we can see which mobile defects we have in our material. The problem is experiments, at least at this kind of scale, as far as I know, can't really see motion at the atomic scale. You can't really see a dislocation moving. But we can now go to the same scale and actually do that in an atomistic simulation. So we can now look at a nanopillar and we can see how dislocations move through these materials. We can look at them and we can look at that from the side and then kind of do the same analysis that we would do in the transmission electron microscope in high resolution TM. So that means we can now find out how these dislocations might move. And I think what's most important to me is we can find the critical configurations where we can then go and be more flexible, do DFT, and actually compare different crystal structures. One of the difficulties we had in this was actually that if we want to look at dislocations and we want to see them in a volume that we've deformed in the computer, then the normal visualization strategies that we just use in, for example, HCP or FCC crystals, they don't work. They're actually not working. They're not geared for these kind of structures. So we spend quite a bit of time now trying to develop the tools so that we can actually highlight where a dislocation is, separate the different but closely related structures, and also analyze the kind of Burgers vectors and defects that we have. So if any one of you are interested in this kind of problem as well, then this has just been published, and probably the more important business for you, the code is also open at Zenodo and should be able to work in Ovito, for example. Right. Once we have this, we can analyze, we can do quantitative analysis on individual slip systems. We need to get faster. And one of the things we are doing to see which slip systems are actually active, even though we have some candidates maybe, is we use indentation coupled with EBSD so that we can then look at slip traces at the surface. They're not unique solutions, but at least they give us some statistics and guide us where to do micropillar compression or in which to actually look at atomistic simulations, for example, in non-basal mechanisms. So for us, that's actually been quite nice the last few years. I know at Imperial you use the very same methods. We can combine experimental and computational nanomechanics, and I think being able to get critical stresses and defect structure from the experiment and combining them with looking at dislocation, motion, and energy barriers in the computer is going to be really, really useful in understanding more about different crystal structures or alloys we want to develop. So that's the kind of summary of what we're up to in this area. I believe we need new materials. We need them for high temperature applications. We might want to combine properties, even improve kind of damage resistance and functional materials. And to do that, we need materials which combine strength, toughness, and maybe some chemical stabilities. There are hundreds of thousands out there in our databases. They're all there. We know a lot of them or have predicted them. I think one thing that's missing is we can't predict the mechanical properties quite yet, or just the modulus. And so this will be our approach for the next 2 years, to look at these fundamental building blocks and then really try and use that knowledge to predict their property, so we can then from a database find and then of course alloy and improve new crystals. Okay, so as I said, I want to give you, because I wasn't asked to speak on a specific topic, I just brought an overview of what we're doing, and I hope that's all right with you. So this was our work on looking at which crystals we might use for future materials. And then of course we work also on current materials that we use, metallic or intermetallic alloys, where we really want to improve the properties, and where we think about normally about, you know, defect design, as you do as well, how we can design the defects, which alloying elements do we need for this. And there was one thing that struck us quite a while ago, is that we have two communities. We either think about thermodynamics, and those people are normally the people who work with phase diagrams and Calvert and design which phases we have in an alloy. And then they're the people who look at defects, and they are mostly concerned with, you know, doing atom probe tomography on one defect, on a dislocation or grain boundaries, seeing where alloying elements go, and then seeing how that correlates with the mechanical properties that we actually get. And so what we thought is that those two should actually go together in something that we have termed defect phase diagrams, or other people have termed this defect phase diagrams as well. And it's a large collaborative project funded by the German Research Foundation. We have about 20 PhD students working on this now. So we are embarking on something new here. I'll also just give you a brief overview of what we think. Maybe there are people in your group as well who work on similar things, and that would be great to combine forces. So our motivation is that what we want to do is we want to really have guided, tailored materials, do materials design for structural materials like in planes, but also for the structure and mechanics of functional materials. And we know exactly what to do for this, right? I think everyone who does kind of undergraduate teaching in materials science, or of course here mostly at least attended these lectures, we tell everyone that's what you do. You look at, you understand your lattice defects like the dislocations, you perform some alloying, and then you have mechanisms like Cottrell clouds or segregation, at least to defects. They might affect microstructure evolution, and you select the phases and their stability from phase diagrams. That's what we do in textbooks and in teaching, and actually in research we go a lot further, and there are a lot of kind of sites that we work on. I've already told you that in ordered crystals, even just knowing which defects we have might be a difficulty. We also know, though, that these defects, when they are alloyed, they are not just some continuous thing like a Cottrell cloud. Actually, you get chemistry and structure interacting very strongly at the defects. We call this a defect phase, as you see. You might have heard the word complexion as well, something, a distinct structure that forms at a defect and not anywhere else. And of course, these will affect microstructural processes like grain boundary mobility. So then you have an effect on microstructure evolution or on plasticity. And the main point that we wanted to look at is, well, actually, we should be able to do that for the defects just the same way as we do that for crystalline phases. So there is a disconnect between those things at the moment. We don't have physical links really between, for example, our structures at a defect and the properties, and we also don't have a coherent framework. Everyone looks at their own material, and we might understand a lot about individual materials, but we don't have a framework where we put in crystalline phases, where we put in alloying, and where we put in how the defects are affected by this. So the first thing to think about, maybe a question, well, does that actually matter, right? Is that actually something that happens a lot of the time, or is that just something that people have pulled out a few materials and published some nice papers on? But actually, we think that this kind of ordering at defects is something that's not the exception, but it actually exists in most materials. And people have looked at this in simulations and also in experiments. Yeah, that you get ordering locally at the defect. The chemistry changes and then the structure changes as well. There must be driving forces for that to happen. It can be at dislocations, it can be at grain boundaries. You can also have phase boundaries, and that will include surfaces where you find distinct structures coming up. So they also must have a thermodynamic stability that has a driving force for this to happen. So the idea is that what we should be doing, or should be setting out to do, is to take these two powerful approaches, thinking about microstructural defects that we tailor and engineer, and think about the phase diagrams that we look at, and really put them together in one new and integrated approach, so that we have defect phase diagrams and not just phase diagrams. That means we have to now do the whole exercise of judging stabilities, comparing different possibilities for defect structures in kind of all dimensions. For example, we have the 3D crystal, or the crystal structure. We also have interfaces at 2D, 1D, we have dislocations, and we also have point defects. And we'll try and put all of these into one framework, really. So the first thing to get clear here is that what we actually understand by a defect phase, so we can put them in something like a defect phase diagram. And we understand by this a structurally and chemically distinct atomic scale configuration at a defect that has a thermodynamic stability, so something that I can affect by changing the temperature, the chemistry of the alloy, and so forth. How will these actually form? Well, what you will get is something that we know from all other defects. You start with newly created defects and maybe a random distribution of alloys of alloy elements depending on how you quenched. And then you have some transient states where the elements will actually segregate to the defect, form the most favorable defect structures. Then you'll probably get some relaxation and formation of defect ensembles, like you get, for example, in recovery. And then at the end of the day, you'll of course not have defects in a kind of long-term thermodynamic consideration. You would have some point defects and two separate crystal structures, right? But the important thing is that we have this in our alloys, and our actually design target is somewhere here. We hardly ever go to actually equilibrium in what we use in everyday life. So this is not our what we want is, and that's important, is that we have local minima here that we can stay in for a long enough time. So we can then, in theory, go and calculate Gibbs energies for the defects. We'll have state variables like the temperature, the pressure, the defect state. We actually need to think about all the different kinds of defects, for example, an edge or a screw dislocations, a boundary orientation, and so forth. And all of these describe the defect phase, and the conditions are essentially described by the chemical potential. And then we need to think about actually doing this, and this is where the problem comes in. There are now a lot of variables or a lot of different defects that we need to look at for two axes, for example, the chemical potential of two alloying elements. So what we think you have to be doing is what you would do in different phase diagrams as well. You have to kind of go and look into your alloy, look at maybe having one defect structure at one point and then having a different defect phase at another point. And then we would have to go and keep looking for other point and kind of look for the boundaries in our phase diagrams, just like you would do for a normal phase diagram. What we'll need then is high throughput experiments and also simulations, and we need to couple the data from all of these different experimental and computational methods. And of course, that's the actual end game. We want to connect mechanisms with properties. So we need the defect, we need the mechanism that it gives rise to, and then we can connect to the properties. We have a strategy for actually populating these defect phase diagrams. One of them is that we do targeted synthesis and that we don't look everywhere, but you kind of do the same strategies as you otherwise have. We think that most of the time when we get a change in defect phase, we'll also get a change in property. That could be the hardness, that could be the structure, and we'll be able to have fast techniques like, for example, indentation for hardness to look for property change. And this is then where we use high resolution methods to do characterization, for example, TEM or atom probe tomography, and where we can also go to different synthesis methods, like, for example, starting with thin film combinatorics and going to targeted synthesis of individual bulk phases with a very, very tightly controlled composition rate. So what we do then is we'll have these defect phase diagrams where we know everything about the defects from high resolution experiments and simulations, and we'll have to connect them with global and local sample conditions, like, for example, the chemical potential around a defect, but not for the whole sample, but you will actually be able to look at this a few microns around it. And then we'll use different methods to look at the properties. For example, for dislocations, we'll again go back to small single crystals and look at how they deform, which mechanisms we get, which stresses we measure, and we can do again the same in the computer. That means at the end of the day that we're really starting here with the assumption that we have some structural and chemical complexity at the atomic scale, meaning these distinct structures that form that are related to a certain structure and chemistry. Once we have these at our kind of point of origin, we can then describe the stability of these individual defects. So we can look at their competition also, and we can connect them to then predict material properties. And we think at the end of the day, hopefully this will be a stepping stone to get a new materials design toolbox to actually be able to tailor materials and, for example, co-tailor them for different mechanisms like corrosion and mechanics. Okay, that was the second part, looking at the thermodynamics of lattice defects. That's very much work in progress. So we are starting out, we're all working at on the same material at the moment, and then hopefully we'll be able to populate one of these ternary phase diagrams and really tailor new materials, or at least in this case, kind of look at the potential of this approach. Now, if you go to materials which are already there, so proper engineering alloys that you're already building cars from, for example, then we might be interested in different things. We might actually be interested in changing not the material so much as self, or only small changes so we can go quickly to application. We might actually be interested in looking at optimizing the microstructure and also the process that we use to make a material. So that could, for example, consider looking at a steel and looking how it performs during deformation, during metal forming. This is again part of a large collaborative project, and here the idea is that really, if we want to have lightweight design, we need to have materials that we don't just consider as we don't go to the yield strength and then we apply some safety, or we don't go to the failure strength and then we apply some safety factor. We also need to know, once we've formed a sheet metal, what kind of local properties are still left. So to really look at damage, but not damage as failure, but damage as something that changes the material properties, and it does it based on the local kind of process history that we had. So if we look at this from a material science perspective that we are taking in this part, we have boundary conditions. We work between material scientists and what we would call materials engineers, mechanical engineers really, who perform the processing. And we have different boundary conditions. I like to think about the microstructure for the material. That's what defines the material for me. For example, here you can see banding in a dual phase steel, the grain size and so forth. And then the engineers, they actually think about the process and the strain path that a material encounters. And we also think about damage, and we think about nucleation, growth, and coalescence. And from the engineer, again, that means how far am I from failure? Which safety margins do I have to consider? And for us, we are interested in the underlying mechanisms. Where do I actually nucleate the first damage, and by which mechanisms do I do this? And then, of course, the important bit here is that I really have a scale bridging problem. Damage might nucleate at the nanoscale, but I need to cover the inhomogeneities that I have at least over the millimeter scale. That could be the thickness of a sheet, and that can also be the strain field or strain path that varies over a much larger area. So what I want to do here is I want to show you how we kind of started addressing this problem. And the first step was being able to combine high resolution to look at individual mechanisms and individual sites, but do this over large areas so that we can actually look at inhomogeneity and get some statistical relevance. What we want to analyze is we want to look at the active damage mechanisms, and we want to learn which ones are dominant and how that might, for example, differ with stress state. So whether I bend a sample or whether I pull on it in one direction or biaxially. The setup that we use for this is that we look at a tensile test sample, and this is a few millimeters, for example, across, and then we set our microscope to take lots of individual images, and at the end of the day, we stitch them together in one panoramic image where you can then, at every point, zoom in to about this level of resolution. That's the one that that looked useful for us. So you can already see in this is actually looking on the top of the sheet. You can see areas where you have, this is a dual phase steel. The bright parts are the martensite. You can see where there are only some islands and a lot of ferrite, and we also have regions where there is a lot of martensite. There were the martensite bands that you saw from the side. So this is one of the reasons why, if we just look at one image like this, we fear we might not be representative enough. So we look at panoramic images that are maybe a square millimeter in size. What do we do then? We then end up with a lot of image data, and what we really need to do is we want to be able to deal with that and concentrate on understanding what the material does and not have people spend all their time looking at micrographs. So we deform a sample, we put the sample together into one panorama, and then we use what you would normally use, some algorithm for void detection. So for example, in case of damage, pores essentially, and cracks, we look for dark pixels that are clustered together. We can quantify those, of course, in terms of the area, for example, or individual size. But what we can also do is we take all of these images and feed them through some image recognition, so deep neural networks. And there are two things we do here. The one is we wanted to separate damage that stems from the material itself, for example, inclusions that have nothing to do with the strain path, and then ductile damage, or better maybe deformation induced damage. And there are two neural networks. The one sorts out the inclusions, which are bigger and look very different, and then the second one characterizes the underlying mechanism for the images that then remain. So this is really the heart of what we do, these two convolutional neural networks that we trained to do that. So our, of course, initial problem was, is that even feasible? I mean, Facebook does that. Facebook does that for, or Google, they do this, but they have much more complex data, but they also have the advantage that they have millions of users or millions of people who label images for them, or big databases that they use. And then there's also the thing is that what were we actually looking for? We didn't want to label a dog licking a chocolate ice cream. We just wanted to label definitions of, or classes of, different types of damage. And you look in the literature and you think, well, that's really easy, right? You have inclusions, and we might not be interested in those unless they have decohesion here, but you can have interface decohesions, you can have decohesions at grain boundaries, or you can have the brittle phase breaking. That's what happens here, and this is what's shown in lots of images as well in the literature for dual phase steels. So that's where we left then, and then we take our panoramic images and we sort out all the little bits. There can be thousands of them in one panorama, so we have fairly big data, and then we want to look at them and classify this data. And sometimes you get images like this, and that's fine, right? You look at this and say, this is a martensite island, it's clearly cracked, so this is what I what I get. And then you think, well, that's easy. I just continue. And you can try this yourself if you like on Menti as well. We've started a bit late, so maybe I will go ahead and kind of do a little spoiler here and show you what we thought. So if you try and do this for different kinds of images, what actually happens is that you also look at a damage site like this. And then maybe if you go back, well, actually, it's not that easy anymore, right? Which kind of damage do we actually have here? I don't know whether, let's just have a quick look, whether any of you actually tried to do this yourselves. Oh, sorry, Microsoft Teams has blocked my browser now, so you can see what's going on if you try this. There are two images in this. I only have one here. If you do this with a lot of people, so for example, in one talk I had 33 people participate, and then actually you get this image. Yeah, this contribution. You have this one image, and well, a few people always decide might be a martensite crack, there might be the interface or a grain boundary that open up. And I also gave the option no idea, which an algorithm would have maybe as well, and that's what you get. So if you can't train humans, if you have so many people, if you have so many options and you can't actually label something and you can't say this is the right solution, then for a neural network you have a problem, right? Because you can't train the computer either them. So then we spent a lot of time having these images, giving them to different people in the lab and seeing what the classes that we needed actually have to be and how we can actually think about this. So for extreme cases, it seems it's not actually that easy. It's always easy to find representative classes that you print in a manuscript. But actually, if you force yourself to want to look at a large global analysis, then it's no longer easy. And so if you want to do this kind of stuff, what we actually found out you have to consider, you need to define exactly what you're looking at. So we wanted to look at the underlying mechanisms. Actually, the research question that we, or the classification task that we ended up giving the algorithm is look at the underlying mechanism for freshly nucleated sites, because our brains tend to kind of infer what we think happened, but a crack that's been just nucleated and a crack that's opened up and deformed the surrounding ferrite, they look very different. So you actually have to define very well what you're looking at. You need to consider your level of resolution. So for example, there will be sites where we simply can't decide based on an image, and we have to be able to classify those together and just accept that this is our resolution level. You have to think about your data set, how complete it is, whether you have rare events that you need to consider. So for this, you can use data augmentation, and you also have to consider your bias. So for example, whether there are sites that you're trying to include but that you really shouldn't, or that, for example, you on purpose only look at nucleation. So to show you just an idea of what we've done with this, we looked at it at this dual phase industrial dual phase steel. We deformed it to different strains, and we wanted to know which mechanisms actually dominates damage here. And we get a number fraction of damage sites. So with this global strain, the number of sites go up nearly about exponentially. So they go from a few hundred to thousands of damage sites over our panoramic image. And what's actually was striking was that initially we are completely dominated by martensite cracking, and then later we get a lot of interface dominated mechanisms later. So if you want to of course avoid damage altogether, you then have to look for the originating at low strain for the martensite, or you might have to engineer the interfaces later to maybe avoid growth as well. We can also use this to help us with in situ experiments, because if we have lots of damage sites that we track for different deformation states and do this in situ in the microscope, then we can go for rare events like the nucleation stage and see whether they've been there in previous images. So we get a lot of these nucleation images or sequences rather than just a few. And we can also, of course, look at evolution for a lot of sites, as you would always do. What we found was what we expected is that 2D imaging just long-term won't be enough to understand the mechanisms, because actually you end up looking at sites like this and then you get half of them which evolve and form bigger cracks as you would expect, and there are a lot of them which don't do anything at all. So clearly the stress state has changed a lot by first deforming a material and then polishing the surface, right? We knew that to start out with. So we think that now that the analysis is automated to a large extent, what we can also do is we can actually go into 3D. So we're now starting to polish our materials and take kind of high resolution, large area maps in each section so that we then get a rich 3D data set. And we already know that this will give us kind of new insights. For example, that the classes we tend to look at, and we just took them from the literature and what we do normally, might not be all that meaningful. It's not that surprising, but it's nice to have kind of confirmation. For example, if you take this same damage site in different slices, so looking from the top here to the bottom, then you go from something that looks like it happens at an interface to something that maybe underneath was actually nucleated based on the martensite crack. So that's something that we really want to dig in now so that we can have a large area, and fairly high resolution, at least in 2 dimensions, and combine this with 3-dimensional information. So to put this together, what we've been trying to do with this approach is to really combine the kind of local scale of initiation and also growth and coalescence of damage sites, depending on the local microstructure, and comparing that with kind of a global view in terms of how, for example, nucleation damage depends on something like the plastic strain. We've looked at that also in terms of growth. So we've also changed triaxiality, looking at different kind of notch samples. They're also done biaxial tests. And you can do all of these with essentially the same trained networks, all the way up to coalescence, because the maps are big, of looking at how the different damage sites then will coalesce into instabilities that will lead to failure. And I think it's actually quite nice because we can now have this method, and it gives us a data set that we're now starting to combine with the people who are doing the modeling. And so we can actually give them more information about the kind of models that we need, more kind of statistics of what, for example, a poor population that they put in should maybe look like from a statistical perspective, and which mechanisms we would expect to take place in the material. And one main insight that we found here really was also that all the damage model that we have, the classical ones, they were actually derived on model materials which had one metallic phase and were fairly isotropic. And what we found was that, of course, in a material where we, for example, combined ferrite and martensite, that locally doesn't hold true. Locally, you're dominated by the local stress state. That's why you need the 3D information as well. But overall, if you look at many damage sites, then actually you find what you expect in a global image. So these models seems to still hold. So we can use them in the process simulation. That, for example, plastic strain is what actually drives nucleation of damage, and the triaxiality, so the overlaid hydrostatic component, is what seems to drive growth of all of them. Okay. So with that, I'll leave you with a short summary just to remind you what I actually talked about. There are 3 bits to this talk. I told you about our approaches to understanding plasticity in mainly intermetallics at the moment, with the aim of then predicting how they deform, and then also maybe finding new phases in databases by having descriptors that relate unit cell structure with mechanical properties. To, on a slightly larger scale, look at how to design defects in different phases using the approaches that we get from phase diagrams and the thermodynamics. So thinking about defect phases rather than just an ideal lattice defect. And lastly, looking at co-deformation, how, when we combine different phases, different materials, how we can look at the mechanisms that define co-deformation in an efficient way, and then, of course, at the end of the day, also find the best processes or the best microstructures. Okay. With that, I think I had about 45 minutes, I was told, which are up now. So with that, I'd like to thank you for your attention. I'd be very happy to answer any questions that you might have.
Thank you. Thank you so much for such an interesting talk. Are there any questions from the audience? I guess I can start with a question. Oh, Dingwei, do you want to ask something?
Yeah. Hi, Sandra. Wow, this is really interesting talk to myself at least, and because I think I find interesting. I have questions for all these three parts. So I start with one.
Cool.
Like for the first one, like the complex intermetallics, you try to split them into different blocks, and by doing this in each different blocks, do they have a similar? They will have some different slip planes, or right? So how would that affect how would that compare with your experimental observed slip system of the real crystal?
Yeah, that's actually a great question because it's one of the difficult bits. So a lot of them tend to be fairly anisotropic as well. So of course it's easiest if they kind of, if a dislocation just stays in one building block. Right.
Yeah.
If, for example, I get, I don't know, now the mouse is gone. But if, for example, I get basal slip in here in this block, and then it won't actually interfere with the other ones. A lot of the time, that's actually what we get. So that's the kind of the first starting point that we're at now. And then we need to understand, of course, once we know what a mechanism we might have in the predominant part of the unit cell, how that interacts when it has to cut through different ones. So there will be clearly two steps in this.
I see. Yes. So anyone, please ask any questions if you like. So for the second part about the defect, does your defect, it will be among different phases, right? So like both intermetallics and matrix, or is it mainly focused on the intermetallics bit?
No, this is actually in both. So we've decided that in order to do this, we need to all look at the same material system. So we're actually looking at magnesium, aluminium, calcium, which I just noticed wasn't even in the talk. I apologize. I feel like you must have felt like when aberration corrected microscopes came out, nobody told you the material that put into the microscope. Sorry. So we're looking at magnesium, aluminium, calcium, which is an interesting alloy system where we can look at ductilization in the magnesium phase, where we found aluminium and calcium go to the defects, go to the stacking fault, and enable non-basal flow. So there are a lot of things still to understand in this. And we also have the Laves phases and other intermetallics there as well. And there is a technically interesting composite. The video I showed you at the beginning, actually, that was a creep-resistant magnesium alloy. But you could thick this up in any kind of any system, and it would be cool to collaborate with people who look at the similar problem but in other alloys, of course.
Yeah. It was that was a great animation in the beginning of the talk. That was absolutely fantastic. And okay, yes. So, but for defects, like comparing the defects in the matrix and the same intermetallic in one alloy, like how to define them? Like I don't know. Like if you have a third axis on this. Yeah.
Yes, exactly. This is why we use the chemical potential, because you kind of, otherwise we started with this image, right? And that's what you get. You then all of a sudden have the temperature and you have the composition, and then essentially you're just in a phase. And then you think you just have the third dimension. And then as soon as you put in two elements, you're completely out of business, of course. And also your global composition is, well, it's a rubbish parameter, right? Your global composition for an alloy that's a eutectic means nothing for a defect that sits in either of the phases. So this is why we then, after a lot of thinking, we went with the chemical potential, because that you can define for a range around the defect. If you at least, anneal your sample to a certain extent, that's an environment around the defect. It doesn't have to be the entire sample. And so you can also put, we think that gives you a starting point to put defects into competition, because again, even if you just use a single phase alloy, you have your alloying species in there, and it kind of has to decide whether it wants to go to a twin boundary or an edge dislocation, right? And that affects the remaining alloying content that you have for further segregation. So this is how we're going to try and put the two together to use the chemical potential, and then we can also have different defects in competition later.
Yeah, I see. Now I remember that slide. Thanks. Sorry, it's another. Yes. So for the last one, it's just a quick, very simple one. So when you do the stitching images, like I know it can be quite automated in terms of translation, like imaging them individually. But for each one, how do you get them focused? Is that also an automatic function in the microscope?
Yes, so over this large image, you have to refocus. Of course, yeah, and luckily, the microscope, once you've kind of figured out where you are roughly, they can, depending on how flat your sample is, I suppose, you have to decide every so many images you might have to refocus. Yeah, so if you look at the training data set for our first work, actually is online as well. If you look at them, they're not all equally nice images.
But yeah, that was really a great method to dig out as much information as we can get from a larger area. Thank you very much.
Thank you, Dingwei. Are there any other questions? I think there's a question in the chat. Thomas, would you like to say the question? So Thomas says that he works in medium.
Hello.
Oh, Thomas is here.
Okay. Yeah, sorry, I was busy. Hello. Excellent talk. I really enjoyed it.
Thank you.
Just a question from myself. So I work in medium manganese steels. I think in Aachen there's a lot of work on that as well. So we know that there's a lot of manganese segregation to dislocations and grain boundaries and stuff like that. So are your models at a state where you can predict how much manganese will segregate to these defects based on the bulk or the global composition?
I mean, this was clearly one of the materials where we started thinking, right? The project is actually with people in Düsseldorf as well, where they looked at this as well. So the idea would be that you can in the future, but we started last year with the actual research. So the idea would be that you can do exactly this, right? That you can kind of predict these local transitions that you then you've seen at these dislocations, right? You get a change in essentially crystal structure changes a little bit at the what's called complexions in the publications for this. Yes, and the models would ideally be able to tell you then which one should form. Of course, the kind of then even greater art would be to get kinetics in there. So for these defect phase diagrams, you would also need something that's more like a TTT diagram, right? That's the two tools that we use. The engineering alloys are hardly ever in equilibrium. But we kind of work with this final point. Yes, that would be the idea, and that you could also predict if you put in another element. That depends on how well we can populate them, or how well you can then do high throughput simulations with more elements at the end of the day. Whether you can also see how you can affect that segregation.
Yeah, that would be amazing.
It'll take a while too. Yeah. Sorry.
No. That's great work. Yeah. Thank you.
Are there any other questions? No, I think thank you so much, Sandra, for giving such a wonderful talk. I'm sure it's interesting and useful for everyone else in this call as well. But yeah, looking forward for more of your work. And yeah, have a good day. Thank you so much.
You too. Thank you very much for the questions and inviting me as well. Have a nice sunny day.
You too. Bye-bye.
Thank you very much.
Bye.